Y is
Oh yeah, how do you, are you going backwards on the Taylor series? Is that like?
you mean here?
Yeah.
Or rather, how are you using 2n plus 1s in
Yeah,
the
how
Taylor
did you
series?
go from u to n equal? How is the expansion of u to n as u to n plus 1?
So u at 2n is delta t before u at 2n minus 2n plus 1, right? So if I draw
Oh, okay, so you're doing the
u as a function of t, yeah, so this is 2n, 2n plus 1, and 2n plus 2, right? So we have a delta t here. We are expanding all of these terms at this point.
Oh, so we're centered on, yeah.
Yeah, we are centered on this point. Okay, so we have all right. Okay, so then the key thing is that du dt at 2n plus 1 is actually different from f evaluated at un plus 1 hat. So basically we have an error term in here that is basically based on a different formula. So when we subtract this, equation 1 from equation 2, what do we get is the error at 2n plus 2, which is the difference between the numerical and analytical solution, would be equal to the error at 2n plus 2 delta t times the error in the f's, right? And if we can assume the error is small, then the error in the f's is basically, let me write as a scalar form, df du times e at step 2n plus 1. Then at the end I still have this, right? Okay, and you can do so this is what we get by analyzing the second formula. We can also do the same thing to the first formula. So let's make this equation 3. And if you do this with the first formula, you can also write down an analytical formula for that. So u of 2n plus 1, okay, would be equal to u of 2n plus delta t times du dt at 2n plus o delta t square, right? So this is the Taylor series expansion of 2n plus 1 at 2n. Notice I'm expanding this formula at a different location as I expanded these two. This is because I'm trying to match this with the first step, the odd step. So once you subtract, so this is from 1 minus 2, and if you subtract 4 from 3, right, this step, what you get is e of 2n plus 1, which is what goes into here, is going to be e at n, okay, and plus the 2n, yeah, right, thanks. So delta t times the du dt at 2n, this is the analytical du dt, which is f of analytical u, and here is f at u to n hat, right? So there is another df du times e to the e at 2n plus o delta t square, right? So look at these two formulas. One has an error of delta t cubed, one has an error of delta t square. All right.
So where's the second?
the worst is actually delta t squared.
Yeah.
But the tricky thing is that this error at 2n plus 1, only appears inside here, which is multiplied by delta t. It actually didn't appear over here. So the carried over term is actually from all these even terms, right? So the contribution of the error in the odd terms only goes into here, which is multiplied by delta t. So that's the magic thing that makes the error in the odd steps that doesn't carry over at the same order into the even terms. All right, it gets so it's okay to have the odd terms being computed at one order lower than the even terms and still get second order accuracy. So this is basically what people have discovered, that you can actually mix some low and high order schemes and still get a relatively high order. So with that, you can actually write this particular scheme as if the odd steps are actually being called the half steps, while the even steps are basically integer steps. So another way to write this formula is to say u at n plus half numerical is equal to un plus half delta t times f of un hat. And then my integer steps, which is the step that is actually second order accurate, is equal to u hat of n plus delta t times f of un plus half. So this is actually another version of the midpoint rule. That is, it's different from the regular midpoint rule. It's one type of the simplest type of Runge-Kutta method. So Runge-Kutta method is basically a mixture of low and high order schemes mixed in a particular way so that the final product at these integer steps are of high order. All right.